Applications of the design equations for continuous flow reactors. In this section, we are going to show that we can size CSTRs and PFRs, that means determine the reactor volumes, from knowledge of the rate of reaction Ra as a function of conversion. When only one reaction is occurring, each of the concentrations can be expressed as a function of the conversion x. Consequently, minus Ra can be expressed as a function of x. A particular simple functional dependence, yet one that occurs often, is the first order dependence in which the rate minus Ra is equal to the product of the rate constant K and the concentration of the reactant A. So minus Ra is equal to Kca, and this is equal to K Ca0 times 1 minus x. K is the specific reaction rate, or also called the rate constant, and is a function of the temperature. Ca0 is the entering concentration. For the first order, the dependence, a plot of the reciprocal of the rate 1 divided by minus Ra as a function of conversion, yields a curve where 1 divided by minus Ra is equal to 1 divided by Kca0 times 1 divided by 1 minus x. If a reaction is carried out isothermally, the rate is usually greatest at the start of the reaction, when the concentration of the reactant is greatest. For example, where there is negligible conversion, x tends to 0. Therefore, 1 minus Ra will be small because Ra is big, so the reciprocal will be small. Near the end of the reaction, when the reactant has been mostly used up, and thus the concentration of A is small, then the conversion is large, the reaction rate will be small, and consequently the inverse 1 divided by minus Ra is large. For irreversible reactions of greater order than zero order, as we approach complete conversion, where all the limiting reactant is used up, by example x equal to 1, the reciprocal rate approach infinity as does the reactor volume. Then, as x tends to 1, minus Ra tends to 0, then 1 divided by minus Ra tends to infinity, and therefore the volume tends to infinity. That's why in the real world we don't try to get a conversion of 1, because in that case we will need a very big reactor. For reversible reactions, example A goes to B and B goes to A, the maximum conversion is the equilibrium conversion, Xe. At equilibrium, the reaction rate is 0. Ra is equivalent to 0. Therefore, As X approaches the XE, the conversion at equilibrium, then RA tends to 0, and then 1 divided by minus RA tends to infinity, and therefore the volume tends to infinity. So for reversible reaction, we don't try to obtain the equilibrium, the conversion at equilibrium, because we will need a very big volume too. And we see that an infinite reactor volume will be also necessary to obtain the exact equilibrium conversion, X equal to Xe. Reactors in series. Many times, reactors are connected in series so that the exit stream of one reactor is the feed stream for another reactor. When this arrangement is used, the conversion X is the total number of moles of A that have reacted up to that point per mole of A fed to the first reactor. And this is only valid if there are no side stream. That means that another flow is coming by another part of the reactor. So if Xi is equal to the total moles of a reactor up to the point I divided by the moles of A fed to the first reactor, then the molar flow rate of A at point I is equal to the moles of A fed to the first reactor minus all the moles of A reactor up to the point I. So FAI is equal to FA0 minus FA0 times Xi. Let us consider three different schemes of reactors in series: two CSTRs, two PFRs, and then a combination of PFR and CSTRs in series. To cite these reactors, we shall use laboratory data that give the reaction rate at different conversions. The first scheme to be considered is the two CSTRs in series. For the first reactor, the rate of disappearance of A minus RA and conversion X1 from the mole balance in the reactor 1, we will have in minus out plus generation is equal to 0. So the reactor 1, we will have FA0 is coming in minus FA1, what is going out, plus the generation, which is the rate of A1 times the volume B1 of the first reactor, that is equal to 0. The molar flow rate of A at point 1 is FA1 equal to FA0 minus FA0 times X1. Combining these two equations and rearranging, we will have that for reactor 1, the volume will be equal B1 equal FA0 times 1 divided by minus RA1, all that times the conversion X1. In the second reactor, the rate of disappearance of A is equal to minus RA2 and is evaluated at the conversion of the exit stream of reactor 2, which is X2. A mole balance on the second reactor will be FA1, the one that is coming from the first reactor, minus FA2, the one that is going out of the second reactor, plus the rate of A2 times the volume of the second reactor, which is B2, and that will be equal to 0. And the molar flow rate of A at point 2 will be FA2 is going to be FA0 minus FA0 times X2. Combining and rearranging these equations, we will have that for the reactor 2, the volume of the reactor 2 will be FA0 divided by minus RA2, all that multiplied by X2 minus X1. So, for the second reaction, we'll recall that minus RA2 is evaluated at X2, and then use X2 minus X1 to calculate B2 at X2. It is important to understand that if the rate of reaction is available or can be obtained only as a function of conversion, that means minus Ra equal a function of x, or if it can be generated by some intermediate calculations, one can design a variety of reactors or a combination of reactors. Space-time. The space-time tau is obtained by dividing the reactor volume by the volumetric flow rate entering the reactor. So tau is equal to the volume of the reactor divided by the volumetric flow rate going into the reactor. The space-time is the time necessary to process one reactor volume of fluid based on entrance conditions. For example, if the volumetric flow rate were 0.01 cubic meters per second and the reactor volume were 0.2 cubic meters, it will result that tau is equal to 0.2 cubic meter, which is the volume of the reactor, divided by 0.01 cubic meters per second, which is the volumetric flow rate, and then tau will be 20 seconds. In the absence of dispersion, the space-time is equal to the mean residence time in the reactor, Tm. This time is the average time the molecule spend in the reactor. Space velocity. The space velocity, Sv, is defined as the relation of V0 divided by V. That means the volumetric flow rate divided by the volume of the reactor. So, the space velocity Sv is the inverse of tau. So, Sv is equal to 1 divided by tau. This parameter might be regarded at first sight as the reciprocal of the space-time. However, there can be a difference in the two quantities definitions. For the space-time, the entering volumetric flow rate is measured at the entrance conditions, but for the space velocity, other conditions are often used.